All right, so let's. I thought it'd be useful to actually just go through slowly and carefully in a video the proof of this simple claim, this first reduction that we started to do in class, namely the informal claim and certainly the intuitive claim that if you have a block cipher that is secure against sprp attackers, then that block cipher is already secure against PRP attackers. This is the informal claim that we made in class, and as we said, this is pretty intuitively obvious just by looking at the fact that attackers in this experiment, the sprp experiment, they just get access to more information about the block cipher than attackers do in the PRP experiment, because here you only get an oracle for the forward direction under E, and here you get oracles for both forward and backwards direction. So certainly, if you have attacks here, or said another way, if there are no good attacks here, that means there are no good attacks that use both the forward and the inverse oracles. Well, then certainly as a subset of that, that means there are no good attacks that just use the forward oracle, which means that there are no good attacks here either. Yeah, this is the intuition behind what will ultimately be the proof of this claim. So to actually prove this, we just think about this claim in other words. So in other words, to break E as an SPRP, as a strong PRP, it suffices to break it as a PRP. Right? This is just a rewording of what we just said. Hence, given an efficient PRP adversary A that gains large PRP advantage, in other words, something that breaks the block cipher as a PRP, then there must be an efficient SPRP adversary B that also gains large advantage. Yeah? And in fact, we already just described what this B is going to look like. If you have an efficient attacker that only needs access to the forward direction of E sub k in order to break E, well, you can pretty much just use that attacker directly to attack the SPRP, right? Because if you break it using one oracle, you can certainly break it using two oracles. So in fact, this is the proof approach for us, is to show that the statement is true, that if you give me an adversary A that's good, then I can build this adversary B that's also good. So here in particular are the steps for our proof goal. So the goal is to construct an SPRP adversary B that has these two oracles. Recall the left oracle and the right oracle. You want to construct this adversary B such that, one, it uses some given PRP adversary as a black box. Yeah? So you want it to be the case that if you want to write basically like the shell of a program that has like a stub for when somebody hands you a subroutine that apparently attacks a block cipher as a PRP. You want to be able to call that thing. So this thing that you construct to use some given PRP, any given PRP, you want it to be the case that no matter what PRP adversary is provided, you can use it. And use it as a black box. So this means that we're going to be using the PRP attacker strictly by like function call. Think of it that way, if you like. We never actually need to look at the internal. We don't need to know what the code is of this PRP attacker. We don't need to know what are the coin flips that it uses internally, if any. We just strictly call it and look at its response. Yeah? So we use it as a black box. Now, we want it to be the case that when we build this adversary B, we don't just want to build it, any which way. We want to actually build it in such a way that it properly simulates the PRP experiment for A. And the reason for that is because, ostensibly, this A that you are being given is good at the PRP experiment. So you want to essentially try to simulate the PRP experiment for A because that's what it's good at. So that brings us to point 3. You want to do the simulation so that B wins the SPRP experiment whenever A would win the simulated PRP experiment, right? So let me say that again. You want it to be the case that if I come up with a way to attack, say, AES in the PRP experiment, that if I hand you this A, you want to build the shell around A that will properly simulate the PRP experiment for this A I've just handed you. Why? Because if you properly simulate it, then this A is supposedly going to do well. It's going to win often. If you perfectly simulate it, then whenever it wins, that means it's guessing the challenge bit in the PRP experiment. And your B that you're constructing around this PRP adversary A needs to win whenever that A would win. Yeah. So you, as we'll see, you want to essentially have B return the same bit guess that A guesses. This is the goal, and this modulo the details of the names of the experiments. This is essentially going to be the way that all of our proofs are going to be constructed. We're going to be handed some supposed adversary that here we're generically calling A. We want to turn it into a new adversary B in such a way that, so we use A as a black box so that we can use any A that's handed to us. It simulates the experiment that A is supposedly good at, and our construction needs to win whenever A would win in its experiment. Now, here I say whenever. It will in fact be the case in the proof we're about to do that the B that we construct will win the SPRP experiment exactly when A wins its PRP experiment. As we get to more sophisticated reductions, in fact, perhaps even in just the very next one that we do, it might be that the B that we construct wins its experiment almost the same, almost whenever A wins its experiment. There may be some small amount of loss, like, let's say that A wins, delta percent of the time, then the B that we construct might win delta minus a tiny, 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 tiny fraction of the time. Yeah, as long as it's close, as long as the thing we construct wins, essentially whenever the thing that we're given does, then we'll have the result that we want. And in particular, that if you are given an attacker, in this case for the PRP experiment, then you've built one that wins a lot in the SPRP experiment, which is exactly what we needed to do. It's exactly what this says. Now, there will be this extra piece, which is that if A only uses a few queries and only runs for a little bit of time, you'll also want it to be the case that B also uses only a few queries and only runs for a little bit of time. You wouldn't actually be saying anything interesting if I gave an efficient A for breaking the PRP experiment, or the PRP security property of E, and then from that, I build a B that does both of these things. It calls A as a black box, and it simulates the experiment, but it runs for an exponential amount of time and asks an exponential number of oracle queries. The reason that's not interesting, it still says that if there exists an A that breaks the block cipher as a PRP, then there exists a B that breaks the block cipher as an SPRP. It still says that. But it's really not saying anything interesting. That's it's almost vacuous at that point, because if you build the B that runs for an exponential amount of time and asks an exponential number of queries, there probably was already a B that runs for an exponential amount of time and asks an exponential number of queries that breaks the block cipher as an SPRP, right? For example, one that does exhaustive key search. And you don't even need the existence of an A that breaks it as a PRP for that to be true. Right? Maybe I give you an A that by some very, very clever computations manages to break AES in the PRP experiment with just a few queries, right? If I take that and I say, okay, fine, the B that I construct is going to run A, but then basically just ignore it and do exhaustive key search. Well, that B is probably going to win, but that B already existed even before I needed the existence of A. So if you have such a reduction where the resources used by A really blow up by the time you get to talking about the resources used by B, you haven't actually done what we wanted, right? We haven't actually said this, that an efficient A results in an efficient B. And that is indeed what we want to support this informal claim. Yeah. So again, before we get into the actual theorem statement and the proof, we're going to build this B from any given A, and we're going to try to very carefully simulate the experiment that A expects so that we kind of capture all of the goodness that A supposedly gives us. And we're going to try to make this B efficient. We're going to try to make it stingy, or make it only run for as long as it has to and only ask as many queries as it has to. All right, so let's let us scroll down. What's happening? Oh God, rainbow pinwheel of death. There we go. So here is the theorem statement that I wrote on the whiteboard. So here's the actual theorem that you'd want to write down. Fix a k and an n that are at least, well, that are greater than 0, and let E with the mapping given, so taking a k-bit input and an n-bit input and outputting an n-bit string, be a block cipher. And as I said, by saying it's a block cipher, that already implies that we know that E has an inverse for every key k, every first input k-bit input k. Let A be a PRP adversary for E. By saying that A is a PRP adversary, we're already implying that A is an adversary that's expecting to take one oracle, and by saying it's an PRP adversary for E, it means that A is expecting to have an oracle that takes in n-bit strings and outputs n-bit strings. So that's all built into saying this. So, letting there be such an A, there exists an SPRP adversary B, which is explicitly constructed in the proof of the theorem, such that the following statement is true. So this statement says that whatever advantage A gets in the POP experiment, this is upper bounded by the advantage that the constructed B will get in the SPRP experiment, possibly scaled by something that we hope is close to 1, and possibly with some additive term here that we also hope is, well, we hope this is much, much less than 1, right? In fact, think for a moment about what this says. If this term ended up being 1, then we'd be saying that the advantage that A gets in the PRP experiment is upper bounded by something that is at least 1. But the advantage is always upper bounded by 1, so that would be a trivial statement to make. So we want any kind of additive term here to be very small, and we want this scaling also to be something like 1. Let's imagine for a second that this thing is 0, and this thing is 1. Then our statement says that A's advantage, whatever it is upper bounded by B's advantage. Hence, whenever A wins, B wins. If it's an upper bound, if it's truly an upper bound, that means that B wins actually more often than A does, which is certainly possible. But in any case, this says, given a good attacker for the PRP notion, I'm giving you a good attacker for the SPRP notion. Hence, breaking E as a PRP suffices to break E as an SPRP. If I turn that on its head, of course, then what I say is, if there does not exist any efficient, if I assume that there does not exist any efficient adversary B or D or F or whatever you want to call it for breaking the SPRP property of E, then that means that this number is small for all of those efficient attackers. And that's an upper bound on this, which means, of course, then there cannot be any efficient attackers for breaking the PRP property. Yeah? So in other words, SPRP security implies PRP security. It's important to think about the direction of this inequality here. And if this inequality were pointing the opposite direction, then we wouldn't have the statement that we want. It's important to think about which way this inequality points. And as a rule of thumb, the way to help guide you for the direction this should point is to think about, we made these informal In class, I said I use this notation that, informally when I want to say this, then equivalently, I can write this more compactly as something like E sprp secure implies E prp secure. And so if you look at the direction that this thing points, that actually tells you almost always which direction this thing should point. So it's sort of pointing this way. So if I were to draw two sort of long arrows here, right, if it's pointing this direction, then you're getting the implication that you want. All right, so this is the theorem that we want to prove. And what will result is we need to figure out what this value is, what this value is. And I was harping on it above a moment ago that we don't want it to be the case that if you give me an efficient A, I build an inefficient B. So we have this, this other part of the theorem statement, which says that, I'll erase that, that if A has running time T, time complexity T, and asks Q queries, so whatever those happen to be, then B has time complexity T prime, which is going to be some function of T, possibly of Q. But whatever it is, we want it to be something that's pretty close to T, because we don't want to run for a lot more time than A does. And B asks QL, which we'll have to figure out, queries to its left oracle, and QR, which we'll have to figure out, queries to its right oracle. Again, we're going to want QL to be, not much bigger than Q, we hope, and likewise QR to be not much bigger than Q. We don't want this to be like 2 to the Q, right? Because in that sense, you have to ask an exponential number of queries. So you got it? This is what we're going to target. So let's think about how we actually do this proof. All right, so let me switch over to this other virtual board. So recall, this is I've pre-drawn a picture here, which will be very helpful as sort of a crutch as you're building your intuition for how to construct adversaries out of other adversaries. So I've got a picture here, and then we're going to fill in some text over here. So let's think for a moment about what it is we're trying to do. I said we wanted to take an adversary A. Now, adversary A, we're told in the theorem statement, is good at the PRP experiment. So here, I've reminded you of what the PRP experiment is. I noticed I've reordered this a little bit from what was in class. It doesn't actually matter. It's the order of these steps. Well, first of all, they're all before the adversary runs, and none of them depends on the one before it, so it's all fine. So here's the PRP experiment. Remember, a key is picked uniformly from the key set for the block cipher. A permutation is picked uniformly from the set of all permutation on n-bit strings. A challenge bit B is picked, and then A is given access to an oracle whose description is down here. The oracle, if B equals 1, the oracle behaves as E with the secret key K. If the oracle's bit is 0, then it behaves as the random permutation pi. A finishes its run by outputting bit B prime, and the experiment returns, this is some new notation, the square bracket. This is the truth value of the statement that's inside. So it's just a compact way of writing the if-then statement. So it returns 1, or true, if B prime equals B, and returns 0 if not. So this is the PRP experiment. Now we've said that what we want to do is make an adversary B that simulates the world, the experiment that A is expecting, right? So A is expecting, first of all, to be connected to some kind of an oracle, script O. It's expecting to be able to ask queries that are n-bit strings to that oracle and get responses that are n-bit strings back from it. Yet, there is no actual oracle, right? We're just handed this piece of code, this black box A, and we know that this is what A is expecting when it runs in order for it to do well at winning the PRP game. But it's not like this oracle comes attached to A. This is just what A is expecting, which is why I've drawn this sort of dotted box here, because it's not really here. But it's our job as constructors of B to simulate this thing if we can. Right? If we perfectly simulate this, then A is getting exactly the environment that it expects. So it will win the simulated PRP experiment as often as, as we're told it does. So our adversary B, well, A is going to run, and A is potentially going to ask some query. So at some point during its run, write this. So, when A runs, during its run, it's, potentially going to ask some query X. Now, we are constructing B, so we have to decide what we're going to do when A outputs some query X. Now, keep in mind, what we want to do is faithfully simulate what this thing is. And the behavior of this, if it was really in the PRP experiment, which we're trying to simulate, would depend on some challenge bit, right? So the actual, in the PRP experiment, this thing is either E sub k, or it's a random permutation pi. That's what this thing is, right? So we want it to be the case that when A correctly guesses which of these two it is, that B, the thing we're constructing, correctly guesses whether or not this oracle is, well, remember in this experiment, this is either E sub k or pi, and this thing is either E sub k inverse or pi, right? Depending on the challenge bit in the SPRP experiment, right? So remember in the SPRP experiment, before whatever this adversary B that we're constructing, before it ever runs, what happens in B's experiment? The key is picked, the permutation is sampled, the challenge bit is sampled, and then B, any B that you provide to the SPRP experiment is given access to two oracles, a left oracle and a right oracle, and the behavior of those depends on the challenge bit that was picked before it ran, determining whether or not these two oracles are E sub k and E sub k inverse, or pi and pi inverse. So we want it to be the case that adversary B, when it runs inside of the SPRP experiment, properly simulates the experiment that A wants. Having said all that, I'm pretty sure you now could figure out what you should do when A runs for B and outputs some query X. Right? We want to simulate either E sub k or pi. And in fact, we have a way to do that. Our experiment provides a way for us to do that. In particular, I can just sort of, let me erase this now because it's not supposed to be here really. It's expected by A to be there. What should we do when A asks a query X? Well, we should just take that X and send it up to our left oracle, right? We just send X up here. So X is passed to the oracle, back comes some value Y. We get a value Y. Now A is waiting for some value to be returned, right? It's expecting that this is an oracle query, so some n-bit string is supposed to come back. What should we do? Well, the obvious thing is just to return it. Send this Y back to A. Why is that a reasonable thing to do? Well, look, if the bit in the SPRP experiment is 1, then the left oracle is E sub k, which means that when A asks X, the response that it gets in return is E sub k of X, which is exactly what it would expect if the challenge bit in its world were 1. Likewise, if the challenge bit in the SPRP experiment that B is playing is 0, then this oracle is instantiated by a random permutation pi. So when A asks X, what comes back is pi of X, which is exactly what A would expect if the challenge bit in the PRP experiment was 0. So we've perfectly simulated, we've perfectly answered the queries that A expects, right? If our bit is 1, it gets an oracle simulation for the PRP bit being 1. If our bit is 0, A gets a perfect simulation of the oracle world when the PRP bit is 0. That's pretty much it. That's how we handle oracle queries. So let's go ahead and start filling in some text over here for our adversary B. First step, we didn't do anything before we started to run A. We didn't need to. So we simply run A. That's the first step. We run A. Now we have to say what we do when A asks a query. So whenever A asks a query X, we'll simply pass that query. So we'll assign to the value Y whatever our left oracle says when we ask it X, and we'll turn Y to A. That's stating verbosely exactly this picture here. Well, we know at some point A is a PRP adversary, so it's going to ask some number of queries X, queries X1, X2, X3, whatever. It's going to ask Q of them apparently, since that's what the theorem statement says. And when it halts, it outputs a bit, right? This is what PRP adversaries do. So it halts by outputting some bit that we'll call prime. We also have to halt and output a bit. What bit should we output? You're probably all saying to yourself, B prime. And that's exactly right. Why does that make sense? Because what? Because we perfectly simulated the environment that A expected, right? When our bit was a 1, it was as if A was playing the PRP experiment with the bit being equal to 1. When our bit was 0, it was as if A was playing the PRP experiment with the bit equal to 0. So if A is good at guessing the bit in the PRP experiment and we perfectly simulated it, we should just take its bit and output it, because the bit in the PRP experiment that we've simulated is exactly the bit in our experiment. So in text, when A halts with output B prime, we should output B prime and halt. That's it. That's the description of our adversary. So this picture is good for helping you to think about how to construct a B from an A. It's very useful to draw these pictures. We'll draw them lots and lots of times until they are sort of like in your head and you can think directly about how the adversary is going to run. And these pictures are quite helpful. So this is our proposed adversary B. That's supposed to be constructed from whatever A you give me. The claim is that whatever advantage A gets in the PRP experiment, the B that we've constructed is going to get advantage that's really close to the advantage that this would get. So this is the particular adversary that we're constructing. And now we have to analyze how well this does. So forget how I laid this out. This way. No, I want to go this way. Yeah. So now we need to, as I say, we must analyze B's SPRP advantage. Yeah, this particular B. So recall the SPRP advantage of B by definition is twice the probability that B wins the SPRP experiment. That the SPRP experiment outputs 1 when B runs inside of it. And then we scale that by scale it by 2, and we subtract 1 in order to keep it in the range, the advantage in the range from 0 to 1. Well, simply rewriting this, we get that the probability that we're interested in is 1/2 the advantage plus 1/2, right? So we write it like this because that makes it clear that this is really the thing that we want to focus on. Now, this is the meat of the analysis. So our goal is going to be to write this in terms of this probability. You want to write the probability that B wins the SPRP experiment in terms of the probability that A wins the PRP experiment. So to remind you, I have rewritten, so this is again the PRP experiment. We just had it on the previous slide. Well, not really, it's off to the left. So I've rewritten it, and here's the oracle. And this is, as I said, this is the experiment A is supposedly good for winning this. This is the experiment in which B runs, right? So this is now the particular B over here that we constructed. So now it's in here. And so with this, this line here means essentially take this code here, this, and drop it in here, right? This is the B that's running. And we want to argue that there's a nice tight relationship between the probability that B wins this experiment and the probability that A wins this experiment. So here's my claim before I scroll down to show you the argument for my claim. I claim that by construction, when B interacts with the PRP experiment, it perfectly simulates, when B interacts with the SPRP experiment, and it perfectly simulates the PRP experiment for A. Right? This is what we were just talking through a moment ago. You can sort of see, if you look at everything that happens before, so this is, B is running everything that happens before B starts. There's a key picked from the set of k-bit strings. There's a permutation picked from the set of permutations over n-bit strings, and a challenge bit is picked. And then B runs, right? Look at the setup for A's experiment. Key is picked from exactly the same set in exactly the same way. A permutation is picked from exactly the same set in exactly the same way. And a challenge bit is picked in exactly the same way. So the entire setup for B's SPRP experiment serves to perfectly simulate the entire setup for the PRP experiment. So up to here, at least, everything, all the simulation is perfect. All of the quantities that are going to be in B's run are exactly the quantities that should be in A's run, with the exception, of course, of the oracles, right? A is expecting to get a single oracle whose behavior, determined by the challenge bit, is either E sub k or pi. B is getting two oracles. This one, recall, I haven't written it, but recall, its behavior is exactly this, right? The left oracle in the SPRP experiment has exactly the behavior of the oracle in the PRP experiment. There's this extra oracle, which gives us the inverse functionality, but you notice that in our construction of B, we never ever call it. We never call this right oracle, right? We only call the left one. So we don't even need to write down the behavior of this thing to be able to understand that our left oracle serves to perfectly simulate the oracle expected in the PRP experiment. Our right oracle, it's superfluous, and we don't even use it. A outputs some bit B prime. Recall that by construction, B outputs exactly the same bit B prime. So indeed, the simulation of the experiment that A expects, which is all the stuff before A runs plus its oracle, it's exactly the same as the it's exactly the same as what B provides. Yeah, this is all the same as this, and the behavior of this oracle is a perfect simulation of the behavior of the expected oracle. So, I claimed by construction. So to really sort of spell this out in detail, when the challenge bit in the SPRP experiment is 1, then the left oracle there is E sub k, and the right oracle is E sub k inverse. And this would imply that the simulated oracle that B gives to A is E sub k. Yeah? And that is indeed the effective challenge bit being 1 in the PRP experiment. Likewise, when the challenge bit in the SPRP experiment is 0, the left oracle is pi, the right oracle is pi inverse. This implies that what's simulated for A is pi, which is giving us an effective challenge bit of 0 in the PRP experiment. This is just making it very clear so that when you come back and look at this again, this video, you see that, yeah, okay, this really lays out all the stuff we were just saying a moment ago. So this, in fact, supports this claim that the construction perfectly simulates the experiment. Also, by construction, we've said that B outputs 1 if and only if A outputs 1, right? We constructed B so that it outputs exactly the same bit that A does. But of course, this implies, because our construction, essentially because of this, that challenge bit of 1 maps to a challenge bit of 1, and a challenge bit of 0 maps to a challenge bit of 0, and the fact that B outputs 1 exactly when A outputs 1, that means that the sprp experiment will output 1, meaning that B guesses the bit properly exactly when the PRP experiment for A would output 1, right? Again, when the bit here, if A guesses that the bit is 1, that means that we, as B, output 1. But a bit of 1 here, if that's the correct guess, is a bit of 1 in the sprp experiment, and vice versa for 0. So that all supports this claim. The probability that the B we've constructed wins the sprp experiment is exactly the probability that A would win the PRP experiment. And that is the heart. This is really pretty much the proof. Yeah? This is the proof, this construction. So now let me go back and actually, so here's the theorem again, right? So what theorem, we need, as I said, we need to fill in this value and this value and these values down here. So let's go over and actually look at what we would write in the proof. And then we'll go back and fill in those values. So here's the proof. The proof starts by giving the construction of B as we just did. Yeah? Give the construction of B. So to remind you, here's the construction of B. So in the proof, you would say, we construct the following B, and you would just give this, just write this. For now, just copy this format exactly. Later on, when we're feeling more confident, we can compact this down, but right now, just write out this form exactly. This is the first thing in this proof, is to give the construction of B. And then you can say, by construction, if you feel like you want to be more explicit to help me to understand that you really know what's going on, you can say and write the sorts of things that we said and wrote a moment ago about how the challenge bits map together and about how the oracle simulation is perfect. But to shorten it up here, because I've already said all that, by construction, this is true. And in fact, I can see this. When I look at the construction of B, I can in fact tell that this is true. And now, given all of the verbosity in the previous slides, you should be able to tell this too. Well, given that this is true, hence, if we take by the definition of the sprp advantage that B gets attacking E, that's just this, by definition. But this, sprp and PRP being the same, means we can make this move, just replacing this by this. But this is just the definition of the PRP advantage that A would get. Hence, this equals this, which is telling us now how to fill in these values. So in fact, these values here, we can get rid of because this thing is actually just 1, right? That goes away. And also, well, this isn't an inequality. I mean, the statement would still be true if we wrote an inequality, but we can be even tighter. This is an equality. And this, there is no additive term. So this is as tight a security bound as you can manage, this equality. Before I go on to filling in these things down here, I want to be very clear about something. The statement says that the PRP advantage is equal to the sprp advantage. But you have to be very clear that because of the setup of the theorem, you're saying that there exists an A, and then we build a B such that this is true. This is still saying that the SPRP security implies the PRP security. It's not saying the other way around. Just because these two things are equal, this doesn't mean that given any B for the SPRP experiment, you could build an A that's good for the PRP experiment. Our proof does not say that. In fact, that's not true. It is not the case that PRP security implies SPRP security. All this theorem says is that SPRP security implies PRP security. So do be very careful. In fact, that's one reason why I often like, when I'm teaching this stuff, to, even if it is an equality, to write it as an inequality, because it helps you to stay clear on what's being shown in this theorem. Nonetheless, this, this I'll leave here sort of in that to remind you, but this is in fact what we've proved, is this equality. All right, so we have to fill in these resources now, and what are those resources? Well, let's look at them. If we think about our construction, every time A asks a query, oh, I've got these backwards actually, don't I? Every time A asks a query, let me fix this, we sent that query directly to the left oracle. And there were no queries made ever to the right oracle. So this should actually be Q sub L, Q sub R. Yeah? Every query that A made got passed directly to the left oracle, and no queries were ever made to the right oracle. So that gives us these two values. And I say that T prime equals to T. And the reason I say that is because if you look at the construction, so let me hide that for a second. If we go back and we look at the construction of B, what does B do? It runs A, yeah? Meaning that it takes, if A runs in time T, then B runs in time T as well. Okay, so our convention, I said in class that I don't really care too much that you are precise about the running time, the running complexity when you do these constructive reduction arguments. One could say, depending on how you fix your time convention, you could say, well, B's running time is the running time of A, which I've been told in the theorem is T, plus the time to respond to these oracle queries. And each of them takes unit time by assumption. So really the time is T plus Q, and one for each oracle query, or even O of Q, if you like. I'm fine if you say that. Alternatively, that's kind of an intuitive convention on time complexity, namely that the running time of A is the running time of A. And anything that you do in addition to what A does costs you more. In particular, oracle queries cost unit time, so you pay 1 unit of time for each of these queries that you ask. That's an intuitive, sort of natural way to define the time complexity. It is, however, a little bit clunky when you're doing more complicated reduction proofs like this. By the way, this thing B that we've constructed is sometimes called a reduction adversary. A less intuitive, but also less clunky when you're doing more sophisticated proofs way to define time complexity is to say that the time complexity of A, in fact, the time complexity of any adversary includes the time to execute the entire experiment that it's in, which would mean that in the case of A, so when you say that A's running time is T, under this less intuitive time complexity convention, you're saying that the running time of A is really the running time for A to run inside of this whole experiment. Now, I say that's less intuitive because you say, well, no, I mean, come on, I'm running A, and A has some number of steps, and why should A be charged if there's a whole bunch of extra crap that happens before it and a whole bunch of extra crap that happens after it? It's true. That's a fair enough statement to make. The response to that is, well, first of all, it makes reductions really easy, because if A's time complexity is the time to run inside of this entire experiment, then it's easy to say that B's time complexity is exactly A's, because B's experiment, we've said, perfectly simulates A's. So it makes the time complexity in the reduction very easy. The other reason why that's a fine convention to make is that in these experiments, the stuff that happens before and the stuff that happens after, it's going to be relatively short time stuff. Yeah, so it's not that it's going to necessarily dominate what A does. So either way, whichever one you feel comfortable with, you want to say running time is running time, and I'm charging in addition for each of these queries 1 unit of time. It's totally fine, and I'll be totally fine if you say that and write the time complexity as such. I'm also totally fine if you want to say, in this example, that B's running time is A's running time. And that's what I've chosen to do when I wrote this theorem statement. So some of you may find that whole discussion to be annoying because I'm not just telling you what to write. I'm sure you're thinking, but just tell me what to do so I get this right when I do the homework assignment. So I am, in fact, I'm sort of giving you some leeway here. I'm saying that if you want to write here, let me just erase this bubble. I would say, under my own personal convention, if you write T, I'm happy with that. Alternatively, if you were to write something like, T plus O of Q, that's okay. I've even accepted in the past things like T plus tiny, small. And the reason is that in all of these reductions, in all the papers that you read, and all of the security proofs that we do, and that are done in the literature to support real-world cryptographic constructions, it will be the case that the things we really care about typically are the oracle queries that are made. And the running time it's extremely rare that the running time of the thing that you build is very much more than the running time of the thing that you started from. So if you can do proofs and you can get the number of queries right and you can get the actual security bound correct, I'm going to be really happy. The running time, if you report it and it's not, don't worry about this too much. Just do the best you can, pick a convention that you like, and go with it. I hope that's at least clear enough. I'm trying to be generous in that respect. Worry about getting the bound and the query complexity correct. In this case, we established that B asks Q queries to its left oracle and 0 queries to its right oracle. And that is the theorem. Yeah? This is the whole theorem. This is the theorem that I would want you to write down if you were writing down this security proof, that sprp security of a block cipher implies PRP security of a block cipher. My hope is by going through all of that, very slow, detailed, long-winded steps, that you can go back and watch this several times through, and it will help you to see more clearly how we're going to do things in subsequent reductions. In fact, I may even just do one more in a video to help you see the same steps again in a different example. In any case, I'll just zoom out here. For the final shot.